Okay, students, today's lesson is about harmonic series and about a P-series test. It's the same objective. I can determine whether a series converges or diverges. We have a special guest star today, and she's here to introduce herself. What is your name, young lady?
Isla.
Isla what?
Isla Galt McAvey.
All right, so Isla Galt McAvey, it's nice to meet you. How old are you, Isla?
I'm 6, but in less than a month I'll be 7.
Less than a week, I think.
Yeah.
Okay. Isla, please tell my students something that they don't already know, maybe a knock-knock joke or something.
Knock, knock.
Who's there?
Alaska.
Alaska who?
Alaska, only one more time to open the door.
Okay. All right. These are the convergence tests you have so far. You have partial sums. Partial sums is when we go to the work of adding up term by term what we have, and that turns into a series, and if this, that turns into a sequence, and if the sequence of partial sums converges, then so does the series. That's a lot of work, though, so we are hoping that there are more convergence tests. The geometric series test only works if you have a geometric series, which means that each term has a common ratio, and it does converge as long as your common ratio is less than 1, and it even converges to a over 1 minus r. The nth term test is kind of nice, except it only shows divergence. It doesn't prove convergence. So if your terms are not going to 0, then you know right away that your series diverges. If they are going to 0, then you don't know anything. The integral test is a little bit more universal test. If you can come up with a function to define your terms and take the integral of that function out to infinity, if that converges, then so does your series. So those are our convergence tests so far. There is a series that is so famous it has a name. It's called the Harmonic series. And Harmonic series famously diverges. So another test is if you can show you have a harmonic series, you can just say, oh, it diverges because it's harmonic. You don't even need to use any proof on that. But here is another proof that the harmonic series diverges. We can prove it with the integral test, but let's prove it without using any calculus. So what we do is we begin with the assumption that it does converge. We're going to say, yeah, it converges, because if we can prove that things go haywire, if we assume that it converges, then that's a proof by contradiction. So let it converges. Let it converge to H. Okay, so we're going to say H is the sum of this series. Okay. Now I'm going to make up a new series, and my new series is also going to start with 1 plus a half. And then the next two terms of my series are going to be a fourth and a fourth. And since a fourth is smaller than a third, that means so far my series is smaller than H. My next two terms are going to be a sixth and a sixth. And so far we have like this term corresponds to this term, but a fourth is smaller than a third. A fifth corresponds to this term, and a sixth is smaller than that. So I don't know if you can see my pattern, but my next one I'm going to do is I'm going to do an eighth plus an eighth. Okay. So this term corresponds to 1/6. They're equal. This term is going to be larger than 1/8 because it's 1/7, and then that term would be equal. So this new series that I came up with is bigger than H. Lied. It's smaller than H because each of my terms is smaller than those terms if they're different at all. So H is bigger than this series that I just made up. But this series that I just made up is also the same thing as 1 plus a half plus, a fourth plus a fourth is a half. Plus a sixth plus a sixth is 2/6 or a third. And an eighth plus an eighth is 2/8 or a fourth. So this new series that I just made up is also almost the harmonic series, except it's a half. So this new series that I just made up is h plus a half. But h is larger than this series, which is equal to h plus a half, so that's nonsense. So this is a proof by contradiction that the harmonic series converges, because we just got to a bunch of garbage. We said h is larger than this series, and we also said that this series is the same thing as h plus a half. Well, you can't be larger and also a half smaller, so that is a proof by contradiction. All right. I would like you to take a minute, pause the video, and do the integral test for all of these. The integral test is pretty quick, so just go ahead and do the integral test for these series. If I do the integral from 1 to infinity of 1 over x to the 5th dx, I get x to the -4th divided by -4 from 1 to infinity, and so that is going to converge because I have 1 over infinity to the 4th, so this one converges. This is the harmonic series. We just did it, but we could also do it with an integral test, and we find that it diverges. And then this one, x to the -1/2, that one would be, if we add 1, that would be x to the 1/2 times 2. And that one is going to diverge because 2 times the square root of infinity would be infinite. So this one diverges. So what we're noticing is that this is going to diverge even worse than this one does, I would say, because it's got 2 times the square root. And so this large exponent down here actually makes our series converge. A small exponent, like a 1, made it diverge, and a 1/2 made it diverge even worse. Okay? So here is the summary, the P-series test. The P refers to the exponent on n, and if your P is bigger than 1, then your series converges. If it's less than or equal to 1, then your series diverges. It's the exponent in the denominator. An exponent in the numerator would for sure diverge if it's bigger than a -1. All right, so here's an example. If I look at this series, this is 1 over 1. This is 1 over 2 squared. This is 1 over 3 squared. Oh, I forgot a term. This is 1 over 4 squared, and this is 1 over 5 squared. And so if you include the term that I forgot, the summation would be 1 over n squared from 1 to infinity. And so this series, by the P-series test, converges. And the proof is P-series with P equal to 2. So as long as it's greater than or equal to 1, greater than 1, it converges. Okay, this one, if I rewrite it slightly, I get 1 over n to the 3rd. And even though I'm starting at 2, it doesn't really matter where I start. This one converges. P-series, P equals 3. That's 3 is greater than 1, so it converges. Okay, this one starts at 20. It's 20 to the 1/2 plus 21 to the 1/2. So it looks like we have the series from k equals 20 to infinity of 1 over k to the 1/2. And so P is 1/2. This one diverges because P equals 1/2. All right, last one. It's already set up beautifully for the P-series test. It diverges because P equals 0.8. All right, that is the P-series test.